Today is Thursday, May 16th, 2024. And I have some news, and I've been looking a bunch into this. We had a class on ocean heat and how infrared radiation does not heat the oceans. It can only penetrate a micron or two into the surface of the oceans. And it just turns out this is not disputed. So what I've learned is that the IPCC, and in fact, if you recall that lesson, I went through 4 papers and showed how they didn't have anything to do with science. It was just models that showed. But you hear all the time that it's getting warmer, there's more CO2, the oceans are warmer, and so that proves it. And there's just this universal hand-waving moment where everyone says the oceans are warmer and there's more CO2, so therefore humans are making the oceans warmer. No one ever says that it has anything to do with downwelling infrared radiation heating the ocean, because everyone knows that's impossible. A few people say, okay, well, that's fine. It makes the air warmer, and so that warmer air mixes heat down into the oceans, and that's what does it. You know, and the best possible scenario there is that it's maybe 1,000 to 1 ratio between incoming sunlight, high frequency sunlight energy going into the ocean, and some kind of mixing that no one can measure. It's just theoretical. It can't be better than 1,000 to 1. So everybody just understands that and waves their hands. Whenever you hear this, whenever anyone says that CO2 is heating the oceans, they cannot answer the question how. Period. Because everyone knows it's impossible. So it's not about climate. It's about using whatever squiggly graphs will convince people to give you their money. And then we'll go back to future, because I meant to start this. We know that the last year was very hot by any measure, and this is not data tampering or fixing by NASA. This is actually the UAH satellite record, which we know and like by our friends at the University of Alabama at Huntsville. And this is the whole lower troposphere. It's about 2,000 feet bulk temperature measurement. That's not just where the weather stations are 6 feet above the ground. And it's gone up a lot in the last 12 months. A lot of high temperature measurements in the last 12 months. What's causing that? Well, according to Javier, there's a pretty simple answer. In 2022, the Hunga Tonga volcano eruption sent about 150,000 metric tons of additional water vapor into the stratosphere. That's about 10% of the water vapor in the stratosphere. That's huge. That's about 4 times the amount of water vapor that the 1991 Mount Pinatubo eruption from the Philippines put into the stratosphere. 4 times. So while many so-called rare events aren't really that rare, and we've talked about that, this one was very rare because it needed just the right conditions. And the condition is that you have a volcano erupting about 150 meters under the ocean surface. If it were less, if it were, say, 50 meters or 80 meters or 20 meters, there'd be much more ash. You're still going to get about the same amount of sulfuric acid, sulfur, but there'd be much more ash if it were shallower. And much less water, because the water it threw up into the atmosphere came from the ocean. And if it were much deeper, it wouldn't have had the power to eject that much water up into the stratosphere. The stratosphere starts at about 10 kilometers. Okay, so this just happened to be perfectly conditioned, and that is rare. Some people estimate it as every 250 years. It would not surprise me if someone found out it was more like every 5,000 years, because we don't know how often these things happen. It's very hard to find the record of such an event in the rocks. right? So Javier says this puts a lot of greenhouse gas into the stratosphere, and the stratosphere is not saturated like the troposphere is, and that's going to reflect or redirect a lot more heat back down and cause the photons, as we know, going the speed of light, to go back down on their journey, and many of them will make it back down to the ground, and then they'll have to come back up again, and that again increases the residence time. This is just greenhouse 101. And that this typically, and we've seen this before, but not as big, but we have Mount Pinatubo and we have records of Krakatoa, typically changes temperature about a year later after the first sulfuric stuff and the particulates do their thing. And then, because that cools, the particulates will cool the earth. That's the first thing that happens. But then after about a year, it gets mixed and it raises the overall temperature, and it will do that for several years, and then the temperature will go back down. So that's Javier's theory. Now, I don't understand it. I understand the words he says. He says it's a very potent greenhouse gas because it's not saturated in the stratosphere. And I understand that he says it's like putting on another overcoat on top of the coat you're wearing, and it's going to cause heat for another 2 years, and then that heat will go back down, and it will be like it never happened in 7 or 8 years. So it's a bubble. It's not climate. It's a meteorological event that affects our temperature for a decade or less, 5, 6, 7 years. I don't know. So I don't get it, because I don't understand how greenhouse gases in the stratosphere can redirect that much energy back down to the surface, because there's a lot of greenhouse gases in the way, and I don't see how they make their way to the surface. So I checked with Will Happer, and I said, Will, I don't get it. I'm confused. Does this really happen? Because Javier doesn't explain how. And he references a paper by an author named Solomon, who says that increasing stratospheric moisture will raise the surface temperature. Decreasing stratospheric moisture will decrease the temperature, will lower the temperature. And this author says that in 2000, the stratospheric moisture level went up by 1%. Sorry, went down by 1%, and that had a cooling effect. So it's all about stratospheric moisture, because there isn't going to be more stratospheric CO2. And this author showed that stratospheric moisture increased in the 90s, which raised temperatures, and then decreased in 2000, which lowered temperatures. Water in the stratosphere. What is the water? It's ice, tiny ice crystals, very small ice crystals. What do we know about tiny ice crystals in the stratosphere? They're going to reflect sunlight. They have to. They're going to increase albedo, right? And so what Javier says, and he says, according to this paper, it overwhelmingly also function, those ice crystals overwhelmingly increase the greenhouse effect because it's not saturated and warms the surface. And that's what gives us this, because it overcomes the albedo effect, because it's so much, reflects so much heat back down. 90% of this is volcano. And if we look at the PDO, we're in an El Nino phase right now, but it's very mild. Yes, it's out of neutral, so it's technically an El Nino. And this is just recent data, but we're in a mild El Nino that is not particularly strong. Also this year, 2024, we had 3 polar vortex breakdowns. Everybody remember this breakdown? What is a breakdown? Somebody, what's the polar vortex breakdown? What does that mean? The polar vortex goes from west to east, right? And when it goes to 0 here, this is driven by, this is temperature here. When warm air comes in, it drops the wind speed to zero. This is one of those sudden stratospheric warming events. Much temperature injection of temperature from the heat pump from the south. High temperature drops, takes the energy out of those stratospheric winds and drops the wind speed, this is wind speed, to zero. And this happened in January. It happened in February, just for a day or two. And then a big one, it reversed the wind speed for about 10 days and they went the other way. And that's this heat in here. You can't really see it. It's kind of covered up. But this is a bunch of heat coming in, sustained heat coming in from the south, from the heat pump. Remember the heat pump, the winter gatekeeper, this happens in winter. Most of the heat escaping the planet at the poles. It gets built up like a battery. It goes into melting ice. And then starting in October or in the dark months, it starts to come out. Right? Heat radiates out through the poles. And here we have quite a bit of heat coming in from the heat pump. And that forces the direction of the wind to turn around and go back to the west for 10 days, for 2 weeks or so. This 3 times in a year is pretty unusual. How many times does this go to zero in 10 years? Anybody? So we have a polar vortex breakdown about 6 times per decade. And in the south, in Antarctica, South Pole, it's 5 times per decade. Remember? 6 times per decade, we should see it hit the line. And we got 3 in 1 year. That's pretty unusual. So we're stacking up some pretty unusual stuff. We got a volcano. We got a medium-sized El Nino that in most years wouldn't drive a whole lot. It wouldn't be particularly exceptional. And we got 3 polar vortex breakdowns in 1 year, 1 season. That's January, February, March. That's pretty unusual. It's not impossible, by the way. It probably happens once a century, that 3 in 1 year. Okay. So a 1 in 100 years event. And finally, we are nearing the peak of 25. And that's another factor to add in to get this. That's just the triple whammy of an El Nino, the shutdown of the polar vortex, eruption of the volcano. And don't forget, we're in a hot phase of the AMO. So maybe 4 things all coming together to make a ridiculously hot year. But most of this is going to be volcano, according to Javier. Now, I said to Will, you know, Will, I'm really sorry. I'm sorry to ask such a dumb question, but I don't get how stratospheric H2O, adding more water to the stratosphere, can raise surface temperature. And he writes back and says, you know what, David, I don't either, to be honest. I don't get that either. Now, he just wrote a huge paper on clouds and the greenhouse effect. So he knows a little bit about this. And he says he doesn't get it. I can only say that I've never seen Javier be wrong. I've also never seen Will Happer be wrong. So I have appealed to a third authority, and that's Richard Lindzen. And I'm having a conversation between Richard Lindzen and Will Happer, and I are, you know, we're asking Dick, we call him Dick, to help us figure this out because he should know. So I will let you know next week because I don't have the data in yet. I don't have the answer in from on high yet. So it's 2 things. Either it's the volcano and I don't know how it works, or it's not the volcano. And what is it? And your guess is as good as mine. I'm stuck on the horns of a dilemma, but next week I hope to have an answer for everybody. Isn't that fun to be working on mysteries in real time? All right, this video is a unit on future climate. And here I'm going to present predictions for the next 200 years of temperature and then for the next 80,000 years or so. Remember that when you talk about climate, you're always talking about time frame. The time frame determines the mechanism. So in the next 100 years, we can rule out orbital mechanics. Instead, we need to look at several factors we've already studied. The first thing to do when predicting the future is to construct a business as usual scenario where whatever caused the past continues to cause the future. It could be wrong, but it's the safest bet because it's the most likely thing that this time it is not different. This time is more like the past. It's what I call the safest bet. Temperature of the Earth has been going up about 1 degree centigrade per century. And so the default assumption should be that it will continue to go up about 1 degree over the next century. And we'll get into some of the factors why that may or may not be true. And this is the Atlantic Multidecadal Oscillation. The AMO has been going for millions of years. It's mostly internally driven by temperature and salinity, so it's effectively just goes up and down and up and down and up and down forever, at least for millions of years until the continents change. And this is not a graph of temperature. This is a cyclic influence on temperature, which is already going up right now. And that explains the previous graph of temperature for the last, this is the slope of that previous graph. Let me start that again. So this is a cyclic influence on temperature, which is already going up as we just saw. And so this has an influence on the shape of that graph if it's already, whatever direction it's underlying is whatever underlying direction it's going. And so this oscillation should contribute to our prediction for the next 100 years. And this is the PDO, the Pacific Decadal Oscillation, which has the El Niños. The El Niños are a response to heat buildup. They occur about every 11 years, but they are very variable in strength, as you can see, and some scientists believe the PDO is a strong driver of our climate. I think of it a little differently. I think the AMO drives our climate, or at least the oscillations of our climate, while the PDO drives our weather. And so strong El Nino events are not predictable on a decadal time scale. So I'm going to assume they're mostly noise and leave them out. Now, let's talk about sunspots, because sunspots are fairly predictable and they come in all kinds of different cycles. There's a 2,500-year Bray cycle, and then another 1,000-year cycle called the Eddy cycle. Now, you see how they both lined up right here during the Little Ice Age. They both were at a minimum at a Little Ice Age, and that caused a grand minima. The Little Ice Age, and it was worldwide because it was about solar insolation at that time. And then 2 more times that same thing happened. And these also have names. These are named minima. When it happened, and also when they coincide on either side. This is a minima, and it has various other characteristics, like it's wider, it's longer at that time, and it has little fluctuations within. And so these are long cycles, but if your time frame is thousands of years, they are very influential. In fact, we can predict from this that the next double low will be in another 5,000 years or so. So here's how the Bray and Eddy cycles have affected temperature over the last 4,000 years. See how they coincided during the Little Ice Age we just mentioned. That reduction in incoming solar energy was a worldwide event. And you can also see how influential the Eddy cycle is. That's the 1,000-year cycle on our temperature. So that's a pretty strong factor, and Javier takes it into account when he makes his prediction of the future, which makes sense. Zooming in a bit, now we see the traditional, well-known 11-year solar cycles, also called the Schwabe cycles of sunspots, and then the Feynman 100-year cycle, which I think is technically about 102 years. So it goes from 1706 to 1810 to 1912 to 2014. And then the next one will be 2016 or so. And this is called F4 coming up in this century. And then another interesting thing we see is that there's always a dent in the middle. there's a low point in the middle between the high points, and it happens every single time. So because it's so predictable, then we predict it for the next one. And I don't know if anybody really knows why that happens, what causes that. This is a double dent and a single dent. It's fascinating. Sunspot cycles are driven by changes in the solar magnetic field as the sun rotates, but I don't think anybody's figured out exactly why it has always a little minimum, a slightly less maximum in the middle of the cycle. This is the Feynman cycle of 100 years. Now, starting here in cycle 25, where we are now, we think that the next 100 years are going to play out a lot like the last 100 years because the Bray and Eddy cycles haven't changed much. This is the Eddy cycle here. And then Zarkova estimates we'll be in a new grand solar minimum for much of this century, starting in here. Well, Vino says he doesn't think that's possible. And I will put my money on the business as usual scenario because it tends to do better. Now, this is the familiar graph we saw at the beginning of the course, but now I've added more sunspot cycles in the AMO. So this is 200 more years of prediction. And let's break this down. Let's get into what we're looking at here. Looking at the past 120, 140 years or so, let's identify what's here. This is thermometer temperatures in black from NOAA, and then in 1980 we switched off to the University of Alabama Huntsville temperature data set for the lower troposphere. So this is temperature. Then importantly, we have the Eddy cycle on its way up. So that could possibly explain the general overall trend of 1 degree per century, that there's just more solar energy as a result of increasing sunspots in general. And then we have the Feynman cycle of 100 years here, which modulates the 11-year Schwabe cycle. But here's the low point in the middle of that. As we can see, it's always right about at the crest of the Feynman cycle. And then the AMO. I'm leaving out the PDO. This is the AMO, and this is actual recorded AMO strengths, AMO index. And we can see that the AMO peaked around 2010 and has been going down. In addition to a minimum of sunspots, that's why we had the pause until the 2016 El Nino, which was here. But in general, you can see that the direction of the AMO is down here, and we're right now just on the cusp of 25. That should end, sunspot cycle 25 should end in December this year or January next year, and that will start heading down. So because the AMO cycle is scheduled to cross the line in about 7 years, and this sunspot numbers will start to decrease next year, we could predict that within a year or two, we're going to start seeing temperatures going down in the short term. And as far as I'm concerned, that's a reasonable prediction. Let's look at what else we're working with here. I've just made up some numbers for the AMO here. It's just a 65-year cycle that I've tried to, sort of estimate reasonably, but it's kind of random. And then these Feynman cycles here have a dent right here. This is strictly made up. It's just a little bit lower here. And then here's another one I made up in the middle of the second one. So this is 200 years. But I want you to notice the Bray cycle. The Bray cycle, which is a very 1,000 years, peaks right here in 2100 and then starts to head down. And we know that 500 years from now, it will have a huge influence and will take temperatures down, or will be a significant factor in reducing temperatures. And right now it's very high. But at the same time, we have the Feynman cycle where we're going to have another low down here in 2115 or 16. We expect another sunspot low. So all these things are going to fight each other a little bit and combine to give us some temperature. And let's see now how Javier predicts that will play out. So this is from Javier's book, chapter 13. And the first thing we see in yellow is the Bray cycle hitting its maximum right here at 2100, just as we saw, and these are the in-between Feynman cycle lows at the end of and beginning of each Feynman cycle. We've had one before that was called the pause. We'll have one again at the beginning of 2100, another pause or something. And here we can see the UN IPCC 4.5, which is kind of their middle prediction of how temperatures will go. This is extremely sensitive to CO2, and I won't talk about it because it's not going to happen. That has nothing to do with reality. But we have two CO2 curves that are important here, and Javier thinks that they will have some influence on temperature. So here we have CO2 emissions, which he says will peak in 2040, 2050. And if the current CO2 craziness continues, maybe it will. But on the other hand, we're really bad at reducing CO2 emissions, even though we keep saying that that's our goal. We keep not doing that. So I don't know. It's anybody's guess. But let's just assume then in 2040 to 2050 that emissions peak and humans figure out how to really make good use of nuclear power, and the rest of the 22nd century is nuclear powered, so that we gradually transition to a nuclear powered future by 2200 more or less. And then the CO2 levels will peak because they're still accruing here, and they will go down just mostly because of absorption by the oceans over time. And then the oceans become less saturated as more CO2 precipitates down into the sediment, and then so the oceans can take up more. This is the number that we're looking at here. This is right now at 420. This number, he says, will peak at about 480 parts per million, and eventually will go down. But again, it does not matter at all. Now, he says that temperature here will go down-ish or flat for a while, and probably because of solar cycle 25-26, that in between will be lower. And then it will go back up to 2060, probably influenced by the strengthening of the sunspots, the possibly positive phase of the AMO at that time, because the AMO will go negative for the next 30 years and then positive for another 30 years. And then he believes that some combination of CO2 and this coming solar minimum will drag temperatures down a bit. And then probably something like the Eddy cycle, the reduced insolation because of sunspots, will end the 22nd century lower, so that the temperature then should be roughly equal to the temperature now. And that's his prediction. And of course, the big unknown here that we kind of can't talk about is albedo. Albedo could have its own driver that's not based on the water cycle. Because if it's the water cycle driving clouds, then that has its own feedback mechanism. And that is most likely just to continue going, and it certainly will. But if it has another way of changing, like nucleation of clouds from aerosols or cosmic rays or some other external influence, then we could see an influence of albedo here, and that could change all this. And all these are very fuzzy numbers anyway, as we know. And my prediction is a little different. And what do I know? I don't know anything. I have no idea what I'm doing, but this is what I'm thinking anyway. I think the AMO is going to be a strong driver, and that the basic backbone of our temperature emissions is more or less the Eddy cycle. So I think that we are going to have a full low driven by the AMO for the next 30 years. This is really just my AMO overlaid on what might be the Eddy cycle here, because we are going to have a minimum at the beginning of the next century, and that's going to start coming down again. So that I think we will probably have a second half of the 21st century that is more or less down, just because of the insolation from sunspots will be decreasing. That's the 200-year forecast. You can place your bets however you like. There are sort of three scenarios. Zarkova says it will go down a lot. Javier says that it will work its way down, and I say that we'll follow the AMO up for a while and then go down maybe a bit later. Not too different. And now we'll look at the next 80,000 years of temperature and just take a rough guess and a quick look at how this will play out. This is chapter 14 of Javier's book. We've learned a lot about what's happened in the past. Now, if we start today, we can see that obliquity and eccentricity are the big drivers, as we know. Precession is kind of a local index on top of those. And we also know that eccentricity will start moving up in another 15,000 years. But in the meantime, obliquity will start crashing down. That means we will start going from just about now a fairly high tilt in the axis to a low tilt, to a more straight up axis of rotation. And that will start bringing temperatures down. The ice sheets are going to come back, and they will start to cover much of North America, Russia, down and through Norwegian Peninsula. The ice will start heading out to sea, and according to Venus, these temperatures we'll start to see the ice really coming down in a measurable way that probably is going only one way, and that's colder, somewhere between 1,500 and 4,000 years from now. Another friend of mine who really studies Milankovitch cycles says that it will possibly happen as soon as 500 years from now. But certainly I would say that by 3,000 years from now, we're just going to have ice that isn't going to go back unless we somehow, fire up our nuclear-powered warmers in 3,000 years and start to build bubbles over our cities or whatever, because it's going to get cold. And 20,000 years from now, it's going to be very cold. And again, we will, unless we interfere. And 20,000 years of evolution is a long time for humans to have the technology we have and to have nuclear power. But ice sheets are going to want to come down and again cover Montreal, Boston, and New York City. And we can expect a pretty serious deep freeze here, as we will also see in Europe and across Asia. Now, during that time, will there be some warm periods? Of course, there will. It's going to fluctuate. And perhaps because of precession, there could even be 2,000 or 3,000 years of not bad temperatures, or some mild, and then it could be much more volatile in another 3,000 years. So I'm not predicting that much resolution. I'm just, Javier and I are both saying that in 20,000 years, it's going to be nice and cold. And you can imagine at that time that we might really need more CO2, because people will have realized that now we're on nuclear power. There's no reason to blame energy companies for anything anymore. And there might be student demonstrations and people gluing themselves to public transportation or whatever we have, drones or whatever, and insisting that we make more CO2 immediately because the plants are going to need it. And then the question of the next interglacial, which according to this, you'd see that we have a less round orbit, a more oval-shaped orbit, and we'll have, again, high obliquity, so that should give us another mild, moderate interglacial, but Javier says it won't. He says that the conditions for the solar insolation, the number of hot days in summer, won't be good enough at that time to beat back the ice, and even though obliquity will be high again, like it is now, it won't be enough to raise temperatures consistently by beating back the ice summer after summer to give us a true interglacial. It's certainly going to be better than here, but it might be much cooler than what we experience now. And on the other hand, he says conditions will be great in 80,000 years, and we will have a real solid interglacial here. Sea levels will again be 100 and something meters below where they are today, possibly. Here's when it's really cold, sea levels will be much lower. So sea levels will go down. Here, sea levels will come back up to maybe around where they are today, but it should be really nice and warm. And maybe finally the people in Canada, if Canada still exists in 80,000 years, will finally have their day in the sun to enjoy full Canadian summers, then very mild Canadian winters possibly. And so my recommendation is that if you're one of these people who wants to be cryo-frozen so that you can be, your brain, say, can be kept on ice until, technology improves and then you can just be uploaded to a computer, or you can somehow live again with just your brain and a new body or whatever. Tell them to wait until 80,000 years from now. Just give it a nice break. Don't let yourself melt during 80,000 years. You're going to have to put up enough money to stay cold for that whole time. But then when you come out, boy, it's going to be really nice. And there's going to be just spectacular weather for a long time at that time. So that's going to be a good time to be born. We'll be in here. And this is going to be a pretty miserable time to be born in about 7 or 8, 10,000 years. Just going to be like no relief for that next 10,000 years, and same again here. And we've been going through that pretty much forever, for as long as there have been hominids. So, and not only are we used to it, but we're better equipped to deal with it. That wraps up a quick look at future temperature. I hope you've enjoyed it. This is essentially the end of our series of lessons, I look forward to more discussions and getting your opinion about what you think will happen, how you think this will play out. Now we go back to our present quandary of where will this go, and I posit to you that there's a lot we don't know, but I don't see why this doesn't maybe even go steeper. I just don't see, like, whatever's driving since 1750 should probably keep driving. And then that's, by the way, this is just great for NGOs that rely on continued emergencies to raise more money. Like, I don't see any bad news for them. I think they've got this business going for a while because we're in a warming period. I don't see any reason why we shouldn't, until what's going to happen that will really turn temperatures back down? Probably a fairly serious minimum, right? Or some orbital mechanics, right? So that could be hundreds of years. I don't know. Any insights here for the next 200 years?
Well, I was wondering why albedo, if albedo's in any of these models, and if there's any information or any theories on cycles in albedo. We've only got 10 years information or 20 years. So I was wondering about that. And I was also wondering about water management on the land, which has happened with agriculture and industrialization, and if that's having an effect on albedo, with fresh water not being able to evaporate because it's being extracted and used.
I don't know. It's a good question. I haven't read anything about it. My guess is that the hydrological cycle is pretty constant. Whatever water gets thrown up is probably just going to come back down. So I'd call that natural variance. Even if we're interfering with it, I'd still call it natural variance, because it has negative feedback, right? There isn't something that just takes that and runs away. You can't put more water into the hydrological cycle and then, it takes off, or you can't have less water going into the hydrological and then it dies out. It doesn't. It just kind of compensates. It looks like for the last, I don't know how many years, albedo has been going down. It looks like for the last 20 years, albedo has been going down. Before that, I don't know. I really like to see a good paper on this, and I haven't. In fact, maybe, in the next week we can try to look, because I think it's an excellent question, Stuart, and I think could be very influential. Mani, go ahead.
Just to ask, what is the point of the exercise of extrapolating into the future?
I mean, really, the answer to why is that we want to deallocate $2 trillion a year that are currently being misallocated and try to use them for better purposes. Anybody else?
Yeah, I was just thinking along those lines for sort of long-term planning for humanity. I mean, obviously, if we know it's thinking of your children's, isn't it? It's not, most people are just tricked into the kind of what's best for me, and emergency crisis kind of reactions.
Since
So,
when did government representatives ever do anything except for themselves?
yeah, exactly. So, I mean, if you look at that, what is it, 20,000 years would pretty much guaranteed a heavy ice age. I mean, that's a very long-term plan. But yeah, what would that look like? Maybe migrating more into the equator, or trying to reverse
It happened. I want to show you my insight in a minute. I had a big insight, and I want to discuss that in a minute. But it happened 20,000 years ago. It's just that, when was the Great Leap Forward? 40,000 years ago, right? From out of Africa into Asia and Europe. So already when we went into the deep freeze 20,000 years ago, people were there, and they probably scampered back to the Middle East. And there's got to be records of this, and there's got to be some, paleontologists who could help us out here. I don't know. It could, for example, be that's what ended the Neanderthals. It just got too cold, for example. I don't know.
Suppose there's always the possibility of some crazy huge comet hitting us out of the blue or something and just throwing everything off. But already prepared.
Yeah, there's all kinds of existential threats. CO2 not being one of them. But yeah. Somebody asked about albedo increasing or decreasing over the past 30, 40 years. The evidence I have on albedo is essentially that the last 20 years we've seen a slight increase in sea mid-layer temperature. I've shown you that graph several times, and it's just outside the margin of error. So it probably is a real signal. So probably the mixed layer and the middle ocean layer down to 2,000 meters probably has gotten a tiny bit warmer. And the only way that can happen is the sun, is more sunlight. And that's the only way that can happen on a 20-year scale, is either sunspots or albedo. Those are the only two things. And so my guess is that sunspots have been going up and down. It's kind of a trough if you look at 20 years. So that might even itself out, but albedo has probably gone up for 20 years. Before that, I don't know. It's very possible that albedo has been going up for 200 years, or that maybe it was going down for 200 years, and it's possible it went up to cause the little ice age. But I think what caused the little ice age was the Maunder minimum of sunspots. So these two things are probably, independent, but very causative. And so I just don't know what the albedo graph looks like for the last 100 years or so. I don't know if anybody does. Shape of the ice crystals affecting albedo. I don't know anything about it, but I can tell you they're very small. There is water vapor in the stratosphere. It does reflect sunlight. Does it have a strong greenhouse effect or not? I don't know. Maybe I got email from Will. Maybe I'll find out here.
Unmute.
No, I haven't heard anything from Will. But next week, I hope to have news on this front next week about the stratospheric. So stay tuned, because I hope to have a short announcement at the beginning of the class. Okay, somebody else?
Yes. Hello.
Who is it? Go ahead.
It's Teresa's husband. Okay, he is here also.
He's free riding. Perfect.
Yeah, sorry.
No worries.
He didn't want to come at the start, but he's here now. He's really interested. Okay, so I'm sorry about the lack of camera. He's just about to say hello and his point.
Hi, David. The thing I was interested in was the frequency of the sunspots and things, 11 years. And it just struck me that maybe what's going on in the sun is that you have nuclear fusion going on, converting hydrogen into helium, producing energy. But the sun's enormous, so there's an enormous gravity field on the sun compressing it all. And what happens is that it takes years and years and years for that force to build up to break through the gravity field. And that's when you get the sunspots and the coronal mass ejections. And when all that's happened, it collapses again. And everything starts again in the center. And that's why you get the 11 to 14 year cycles.
And it's a pressure cooker, you said?
It's like a pressure cooker.
I don't.
It builds up, releases, compacts again. And
I don't understand that. Let me just ask, because we all know how long it takes a photon to get from the center of the sun to the surface of the sun. How long is it, class? You got to unmute. You got to unmute.
100,000 years.
150,000
50,000 years.
150,000 years on average for a photon to make its way from the nuclear fusion event to the surface of the sun. So I don't understand where the 11-year cycle comes from.
Because that's the photons going out, but you're left with the helium atoms getting bigger and bigger and bigger. And then you get a huge amount of them, and the gravitational effect pulls them in. And that's what stops everything happening.
What makes that 11 years, though? How does that? Why is
I don't know how long it would take. It's how big the sun is. But it seems to me that what's happening is that things are sort of pushing and releasing, pushing and releasing.
I see. That's okay. Okay.
I'd call that homeostasis.
Okay, there's a problem though, because we know that for almost 150 years, there were almost no sunspots in the 1500s and 1600s.
Well, I'm not saying it would be automatic every time. It depends all the perturbations in the sun.
Well, you didn't come up with this theory. You read it somewhere?
No, okay. I came up with you listening today. It's a pressure cooker.
So there are a lot of solar scientists, and I'm sure people have written about this, if not papers, possibly. I mean, if not books, certainly papers. So there are people who've really looked into this, and I'd be fascinated to learn if you have anything to report. There's plenty of work on this because people really like.
The only problem is I did a degree in mathematical physics 50 years ago.
Oh, there's going to be papers. Go to scholar.google.com. There's going to be papers on it. What causes the sunspot cycle? There's going to be a lot on it. Yeah. Zarkova, she's probably talked to Tom Nelson about it. I don't know. I'd be interested to know.
Yeah, I don't know, but I've always been intrigued as to why sunspots have this regularity as to what's going on.
On money, it's 8 minutes, dear. Oh, yeah. I forgot. Yeah, that's okay. No points off. I'd be very interested and would love, you're welcome to come back and give us a 10-minute report. Have as many minutes as you need. I have no clue what causes sunspots.
No. Well, maybe that's...
But some people do. The solar scientists are probably having, conferences and talking about it all the time.
He has to come back in another lifetime to continue the research.
Me too.
Well, because he wasn't, it wasn't available. There was nothing available then, was there? And this has really been very inspiring for him to wake up to stuff. It's great.
Sure. I mean, he's welcome to watch all our videos. Of course.
Yeah.
Sure. But scholar.google.com, what causes sunspots? I'm assigning that to anybody who will accept it. And bring us back.
According to NASA, sunspots are caused by the magnetic field of the sun, and that flips every 11 years.
Yeah.
And so you've got a cycle of highs and lows related to the strength of the magnetic field.
Right. Is it really flips every 11 years? I read something about it.
Yes.
Yeah.
That's what they're saying.
There we go. So that's a big part.
Causes the magnetic field to flip is the energy from the fusion reactions.
Or it's angular momentum. Anything that's regular like that probably has a lot to do with angular momentum.
Yeah, but so does nuclear fusion.
I just don't know what would cause an 11-year cycle. So that's the question, is like there's going to be good stuff on this. Let's dig into we can have a committee.
Yeah, that would be great. Thank you.
But you got to realize that it doesn't happen every 11 years, and that there are sometimes 100 years where there are almost none. So, what causes that? And is that related? Does that not flip on the sun then? I mean, we need the research, because I don't have it. I'm too busy trying to figure out stratospheric water vapor. Anybody have? Yeah, so please, solar research. It's exciting. Other comments or questions about what we've done? 10 lessons, and we've gone from 4.5 billion years ago to 80,000 years from now. Not too bad. Not too bad. I personally look forward to these times together, because I think it's a lot of fun. I hope you guys do too.
Yeah. I have to go back to the 1976 thing, because my husband, who's just been speaking, has said there were some wind changey things. I have no idea what he's talking about. But 1976 is the year we got married, and we are still actually here. That's quite something, isn't it, really? But anyway, it was the end of this really hot summer. 1976 was renowned, and then we had a wedding. It was a very sunny day, and then the rain started. I'm not quite sure whether it was the next day but it was very soon afterwards. Chris has said there's something. There were sort of changes in the wind movements or something. I don't know. If you could sort of float something into your next thing, that would be great.
I am looking at the El Niños right now, and I don't see a big El Nino in 76. I see
19. We're not old. 1976.
Yeah, 1976.
Oh, yes, I thought you said 18. Yeah.
No, here it is. I'll show you.
Yeah, let's see.
I'll show you. And this is the cumulative graph, and not the individual, but the individuals are here. You just have to look at them. Here's 1970.
Yeah.
70 here, 75, 76. So here's an El Nino. It's not a particularly big one. 98 was the big one.
Mm-hmm.
That was the big one. That was the one that Al Gore used to kick off his little industry. 76 is here. But there are kind of any number of other things. Don't forget the AMO at that time was in a negative phase. Actually, it was very negative. Look at that. 1976, it was very negative in the AMO. So, you know what? This really brings up a good point, though, Teresa, that people think of their local temperatures or conditions as, as global. And, for example, people say, well, there were ice fares on the Thames for 150 years during the Little Ice Age. It's true, but it has a lot to do with pressure systems, and the difference between freezing and not freezing of water, is a very small perturbation in the temperature that maybe, 100 miles away or just across the channel or somewhere else didn't have those same conditions. So we can't generalize a phenomenon and say, if we said to ourselves, well, it was much warmer 9,000 years ago. Well, how do we know that? Well, for example, the tree lines from 9,000 years ago, all around the whole Arctic and down in Antarctica, have much higher tree lines of petrified wood. All right, so that's a global phenomenon, right? But be careful to think that your local phenomenon, because it's driven by pressure systems. Air and water pressure systems is really what drives our climate. And so those are if you looked at those from like in real time from a satellite, you just see all kinds, you know, in the way that the balloonists look up at the air and they see things we can't, because they know it's going this way at this altitude, but this way at this altitude, right? It's very much more variable and mixed and different than our mental models of it really are, right? It's on every scale, from one valley to the next, from one mountain range to the next, from one body of water to the next, from one latitude to the next. The pressure systems change a lot.
It's very complicated, isn't it?
It's also complex in that it's interdependent. And so there's a lot of, complex adaptive behavior. When cold air comes down from the north, when warm air goes up into the Arctic Circle, cold air comes down and we get a freezing cold Madrid, and everybody complains about it, but that, yeah, sure. But then Oslo had fantastically warm weather or whatever, it's very complex.
Indeed. Okay. Thank you.
Yeah. So then those events, those particularly El Nino events, I think are very hard to predict. And so it's noise. People say it's a big deal and it's so hot and everything, but it's really just noise. It doesn't raise any money for campaigners, so they don't want to know that, but that's what it really is. All right, I want to talk about.
Excuse me.
Yeah, go ahead.
Michael asked a question about glacial, interglacial. Is there a non-glacial period?
Well, no, because we have these Milankovitch cycles that are driven by orbital momentum that are always cycling, right? So there are times when they line up and you get a big glacial or big interglacial, and there are times when they kind of cancel each other out and you have less of a glacial, but it's not what I would call a non-glacial, or it's fairly predictable on the scale of 20,000 years or 10,000 years. It's fairly predictable. You can these cycles are always cycling, and so you shouldn't be surprised to learn that they line up and there's an extreme. It's like the tides, sometimes they offset and sometimes they magnify. So it's maybe more of a word usage that you're using, but I'm just trying to explain that there's no kind of exceptions where, it just flattens out for 100,000 years. No, because this is all orbital momentum. Does that make sense? You still look puzzled.
David, has there been a time when there's been no ice on the Earth? That's kind of like my question.
Sure. Yes.
And what would we call that?
50 million years ago, it was very hot. If you remember when we showed when there was an equatorial current all the way around, when there was all the continents were different, and the Middle East, where's my Middle East? Hadn't opened up yet. I can't find the Middle East because it's backwards. When there was no Mediterranean, I don't know where it is, but the whole thing flowed pretty much all around the equator. Then heat really built up. And then we had palm trees on the poles and dinosaurs. The dinosaurs were gone by 50 million years ago. So 50 million, I think we had giant sloths and other animal and palm trees on both poles.
So in that case, we are not going to have another period without ice.
The continents will change. Just depends on your time period. In 80,000 years, our continents won't be too different. Our continents maybe can move a mile or something, or 10 miles, I don't know, in 80,000 years. Not enough to reshape the current, the water currents, the ocean currents. Okay. But in 20 million years, it could be a whole different story. I don't know. There's several videos showing the continental drift over the next 20, 50, 100 million years. And it's just a guess. It's just computer models. Who knows? It's better than I can guess, but it's still a guess. Yeah, so we're in a current regime that we've been into, remember, for about 14 million years, right? Since the Isthmus of Panama closed. And I don't know how long that regime will last, but when it changes, the whole pressure system thing will change. All of this stuff will change. In other words, as Javier would put it, the Earth's reaction to the orbital mechanics aren't going to change, but the Earth's reaction will change because that's going to depend on the shapes of the continents. Right. Also, the length of day will change a bit over 20 million years. Right. A bunch of things will change on that order. It's a whole different set of drivers when you start to look at millions of years. 500 million years, we're all gone. You know, the oceans will cook. So make your plans now. I'd go for the 80,000 year vacation plan. I think that's my plan. get cryo frozen, get your brain frozen, and then tell them to hang on. It's gonna, I guess, be a little expensive to keep you on ice for 80,000 years, but you hope there aren't any mistakes with the plumbing or the electricity for 80,000 years so that you don't melt. As several cryogenically frozen clients have, unfortunately, and they had to be tossed in the dumpster because they were no longer frozen. I want to ask now, I've got, we've kind of covered the time, but I just want to take 10 or 15 minutes. Now that we've done 10 classes and kind of wrapped up from 4.5 billion years ago to 80,000 years, what has been your big insight? What is different about you now? What was it that gelled or that came to you during this time that's kind of the number one thing? Who wants to start? Anybody?
Yeah, I think for me it was probably the photon analogy, because for me it's kind of, if you try and think of it as a big picture, it's just light interacting with matter and coming back out again. And when you mentioned that point of where it's kind of always in a almost equilibrium, there's either slightly more coming in or slightly coming out. So I quite like thinking in that sort of big picture way, and then all the details are like just what happens in between with all the matter that gets stuck in the middle.
All right, excellent. Okay, anybody else? Next.
For me, it's the fact that there's so much is unknown that the IPCC must be full of crap. And so, just today we were talking about more stuff that is just not understood. So, that I think that's really the key for anybody that's only getting sort of half an understanding of what's going on here, which is probably most of us, because it's such a complex area. That's got to be the key. If we're speaking to people, that's got to be the key point that we're making, hasn't it? Because when the science isn't understood by the people, you said earlier, you asked somebody, I can't remember what it was you asked, but you asked them for an answer. It was about why the ground heated under certain circumstances, and they didn't know. Well, if they don't know and they're the experts and they're writing scientific papers on this, how can anybody know? And if there's this amount of stuff which is simply not known, how can anybody make any rational prediction about the future? So it's all just, I'm going to not say the word.
Plus there's people getting paid to pump out ridiculous papers and predictions,
right?
And graphs and charts. And we saw the Woods Hole image of the ocean heating, and that was all just nonsense. So there's just tremendous amount of that. But yeah, you got to imagine that 30 years ago or 20 years ago, they said, we got to really dumb this down. We got to make it about one thing. Two things is too complex for the average, for the Guardian, journalists. let's get it down to one thing. All right, what do you think? Well, I was thinking CO2. That's a good one. That sounds great. What is CO2? I don't know, but let's go with that. That might have been the conversation in about 1990. Anybody else have a realization?
Well, I'm just glad that because I really thought that CO2 and plus methane would lead to global warming of a kind which would be catastrophic for people. It seemed to make sense because if the property of CO2 is to warm the atmosphere and then it just gets faster and faster to do with feedback effects, then people are in for a very bad time. So intuitively, I've departed from that position and from other and for other reasons. So I'm very glad to have learned that there's obliquity precession, sunspots, AMO, etc., which would indicate that that theory is very limited and probably wrong.
No,
So
but
I'm
if you
fine.
give us your money, we'll fix it.
Sorry?
If you just give us your money, we'll take care of it. We'll make sure that that doesn't happen.
Yeah, I went to a thing called a Nature and Climate Festival last year. Some people actually know. And I said, oh, yes, I used to be a road protester. They said, oh, you're a hero of the revolution. Thank you very much for everything you've done for ecology. So I got up and said, actually, I don't think it's true anymore. So my welcome was a little less warm than it had been. But I suggested to them, would you like to hear the other point of view? Well, no, they wouldn't. Which is very sad because they're kind of, they're kind of bright people. So it's very sad, but I will ask them again.
What, King Charles, please, would you like to have a conversation about climate science? No, I wouldn't. I'm too busy trying to save the planet. Thank you very much. I only have limited time left. I've got to do everything I can to save us from Armageddon. No time for scientific conversations. Anybody else have a big aha moment?
The one thing I keep remembering is, and it just keeps going through my mind, is that temperature leads CO2 and not the other way around. And that the lag is so long, it's 800 years. It's just so profound. And you can pretty much stop anyone in their tracks with that statement.
Oh, no, because this time is different.
Well, I had a friend, you asked me,
have this down.
You asked me to say if I'd ever changed anyone's mind. Well, I had a friend round last weekend who we generally joust about everything and anything. And when he came round, he told me what an idiot I was not to accept there's a climate crisis. And when he left, he said, no, there isn't a crisis.
Hey.
Record that conversation. Write it down. Tell us.
He is a writer. He may well write a story about it. I don't know. I'll let you know if he does.
He can interview all of us, any of us. I would love to see. I'd love to see stories of people changing their minds. When I changed my mind, I wrote a big piece on Medium that 70,000 people read. Did that change any minds? I don't think so. But I think that's
the conversation got heated. And it got I wouldn't say nasty, but there had to be some sneering involved. And some put down as well, in that I just kept saying, but you're wrong. You're utterly wrong. Now, can you not get off your backside and go and find out? And of course, the answer is no, 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 no. But so, there's a point where I'm telling people, you're just so wrong. It's frightening. And in that tone, really.
When they say everybody knows, I say, yeah, in 1800, everybody knew you should beat your children to keep them in line. Everybody knew that.
Yeah.
Everyone knew that. It was the only way. That's just common sense. Any other big realizations? I will give mine. Stuart, do you have one?
the CO2 does change the climate. I thought it made no difference at all. Yeah. And all the cycles, and that it's something that we can learn if we read that book a couple of times. We can, we can get an idea of what the factors are.
Yeah, CO2 is responsible for life on Earth. The first 100 parts per million are very, very important. And that's why our deserts don't freeze solid overnight. It's why our whole planet can support life. Somebody changed his mind?
Can I have a little sorry about broken camera. But I'm quite a shy person normally, and I don't speak out loud very often.
Okay.
So this is quite amazing, right? Let's go with that to start with. And one of the things that we, a meditation type group thing that happened a couple of days ago, and what I realized is that when you try and learn a foreign language, which clearly many of us have gone through this process here, and me particularly, you can start to understand what people are saying, but you can't actually speak it out loud until much, much later when you practice a bit and everything else. And you can't say it. So I have learned much during this course. And thank you very much. But clearly, a way to go, many ways to go beyond that. So that if I have to do a 2-minute presentation, that would be almost, have I done 30 seconds? Will that do?
Sure. Whatever you think. Sure. Show us.
The
best way to learn something is to teach it to others. So teach us something.
Oh, yes. Okay. Well, yes, we had some local research here, which maybe I can use as my example without going into everything else.
Solar influence.
Well, it was about water and flooding and but anyway, maybe I can excuse me doing about a minute rather than several minutes. Would that be okay?
Just teach us something. I don't care how long it takes.
Well, thank you very much.
Sure. Anybody else? An aha moment, a realization?
I think the fact that CO2 is like really good and we should have more of it was quite funny for me, because it's kind of just thinking, well, that's turned everything on its head.
Excellent. It's where this comes from.
Yeah, exactly. Gas of life, isn't it? That Will Happer video you shared. A good one, man.
Need it. All right, I'd like to do mine.
I do need to add a little something. Joe Walton has been here in the times that I have been here, and I love his penumbra. Is that the right word? I don't know. He's exuding the sun's energy.
Well, I can tell you what that is. It's actually
a black hole.
A black hole, yeah. I really like the image.
Yes, thank you. It's like, I all I got from it was exuding sun's energy. Well, black holes normally do that. So maybe you can tell us more about that.
I really like the image because I found if you get it big on your screen and kind of just relax your eyes and look at it, it almost starts vibrating. I thought it was pretty cool, so that's why I chose it.
Absolutely, it's been it's one of the things that's I've been impressed about. So thank you very much.
Nice. No worries.
Now, does everybody have another 10 minutes, or should I wait and do my aha moment next week? Maybe. Should I wait? Do it now. Do it now.
Do it next week.
All right.
Well, I'm just going to vote for next week.
Mike says, we have time, so or even I'll do it in 2 weeks, because next week we've got a lot to do. Let me do that. Next week we are doing Bayesian reasoning and critical thinking, and it will be challenging. So drink your green juice or have your special cup of coffee or whatever it is, because you will see, Unmani, that it will be very challenging to your brain, and it will help us reveal some of our weak spots and see that there is a world of evidence-based thinking that lays ahead if anybody wants to explore that world. And I have given a little bit, coffee, whatever, exotic mushrooms, whatever you need. I've given a little taste of that in something I put on the community for, I think, assignments to read an essay that I wrote. The essay is very large. It will take hours to read just from start to finish, but have a look at it and try to spend a little time with it because it's about epistemology. Epistemology is how we think about thinking. And as I say, I've kind of uploaded to the web about 1/3 of my epistemology, and it's all sitting there waiting for you to come discover it. So it's in the assignment section. Have a look at that and then be sharp, and I'll see you next Thursday.